Hi guys, in this video we'll take a look at the need for the chain rule and composite functions, related rates of change, examples, and then we'll finish with a summary.
So what is the need for the so-called chain rule? Consider the area of a circle that is expanding. So we have an expanding circle, and by that we mean that the radius of the circle is increasing in some way. Using the area of the circle, we can relate the area to the radius. We have that the area A is equal to the constant pi multiplied by r squared. Differentiating this will tell us how the area of the circle is changing with respect to its radius. We can find dA by dr. And by differentiating our expression for A in terms of r, we get 2 pi r for our derivative. However, we are more interested in finding out how the area of the circle is changing over time. So we'd like to be able to find out what dA by dt is. But for this, we're going to need slightly more information. We can find a variable's rate of change with respect to a certain variable by relating it to other rates of changes using what's called the chain rule. So in particular, if you know the expressions for dA by dr as well as dr by dt, then we are able to use the process known as the chain rule in order to calculate an expression for dA by dt. We are able to calculate more complicated rates of change with the help of certain rules involving the chain rule. For example, if we want to differentiate in general the function f of g of x, i.e. a composite function, then we do this using the chain rule. So what exactly is the chain rule and how can we apply it to composite functions? We can use the chain rule to differentiate composite functions. A function of the form f of g of x. In particular, the function g of x is inside the function f of x. And so, as we've seen before in algebra and functions, a composite function is a function of another function or a function in which another function exists. Consider the following function. Y is equal to 2 multiplied by x to the power of 4 plus 1 all to the power of 5. It can be made into a composite function by letting u equal 2x to the power of 4 plus 1. Currently we have our y, which is equal to 2 multiplied by x to the power of 4 plus 1, and then all of this is to the power of 5. Well, if we let u be this quantity, 2x to the power of 4 plus 1, then this quantity, 2x to the power of 4 plus 1 all to the power of 5, is going to become equal to u to the power of 5, quite simply. And so we have our inside function, which is our 2x to the power of 4 plus 1, and then our outside function, which is x to the power of 5, the function that takes x and takes it to the power of 5. Now in general, we may be asked to then find dy by dx, which would be a tedious process if we took the normal route of differentiation. Now if we were to differentiate this function using our normal route of differentiation, we would take our y, which is equal to 2x to the power of 4 plus 1 all to the power of 5, and then we would expand this out, and we would get as our first term 2x to the power of 4 all to the power of 5, and so on. And then we could differentiate all of the terms term by term, and this would give us our result. However, this is quite a tedious process, and imagine if this power 5 was significantly larger, say 100, then the expansion would be quite difficult. And so we'd like a more direct method. Instead, we can find the derivatives of the two different functions. We start with our y, which is in terms currently of u, and is u to the power of 5. If we find dy by du, which we do by differentiating this function with respect to u, and so we get 5 multiplied by u to the power of 4, then we can differentiate our overall function quite quickly. We also take our u, which by definition is 2x to the power of 4 plus 1, and we differentiate that with respect to x. And so we get du by dx is equal to, by differentiating, simply 8x to the power of 3, because the plus 1 differentiates to 0. Now, if we treat the derivatives like fractions, we can see how dy by dx can be formed from dy by du and du by dx. Consider our dy by dx. This is what we'd like to find. Now, if we write out dy by du and then du by dx, in the event that we can treat these two derivatives like fractions, we can see that if we were to multiply them together, these du's would effectively cancel out. And therefore, you're just left with dy divided by dx, which gives us what we want. Now, we can't read and do this, it's not very rigorous, but it turns out this is the correct rule, and it's the right way of thinking about it. We can find dy by dx using this and the derivatives that we have previously found. So again, we have that dy by dx can be almost expanded as dy by du multiplied by du by dx. And therefore, we can find dy by dx by using our results from above. We get that dy by dx, we'll have to refer back to our results for dy by du and du by dx. Dy by du is 5u to the power of 4, and du by dx is 8x cubed. And so by multiplying these together, we get a 5u to the power of 4 multiplied by an 8x to the power of 3. By bringing the constants together, we get a 40, and then we have this x cubed, and then we have our u to the power of 4. Well, by resubstituting what u actually is in terms of x, u is 2x to the power of 4 plus 1. And so we get a multiplication by 2x to the power of 4 plus 1, all to the power of 4. And so this is the result for our differentiation. This rule can be used to differentiate functions of this form, i.e. composition of functions, quite nicely without having to expand or otherwise. This treatment of derivatives like fractions can be summarised by the general formula used to describe the chain rule. Given y, and we'd like to find dy by dx, we can do so by multiplying together dy by du and du by dx. And again, specifically, what we do is we take y to be a function of u, and then we take u to be a function of x. At the end, we resubstitute back in our u in terms of x to get the entire result in terms of x. This is the chain rule. So how can we deal with related rates of change using the chain rule? The chain rule can be used to connect rates of change in situations that involve more than two variables. A rate of change is a quantity used to describe how a variable is changing in relation to another variable. For instance, we can find the rate of change of the area of an expanding circle with respect to time. Now, the first thing we need to do is to identify how our radius r of the expanding circle is changing with time. And suppose that we're given in particular that at a time t, the radius r is equal to t squared plus 1. So again, at a given moment, we have a circle which has radius r, and so we have these following coordinates on the xy plane. Of course, the radius will be drawn on as r at this point. The circle is expanding, and at a given moment, it has an area A. Now, as we've seen, we can write A in terms of r, such that a is equal to pi multiplied by r squared. Now in this rather simple situation, we could substitute in our expression for r in terms of t in order to find dA by dt, but in fact it is unnecessary. First we calculate dr by dt. Differentiating our expression for r in terms of t just gives us 2t. The plus 1 differentiates to 0. And similarly, we can calculate our dA by dr. This is quite simple, we've seen this before, we just get 2 pi r. And then by the chain rule, if we'd like to calculate dA by dt, then we do this by having dA by dr multiplied by dr by dt. And then quite simply, we get as our expression for dA by dt, just by substituting in our results we found above, dA by dr is 2 pi r, so that comes first, and then we'll put a bracket around all of that, because we're going to multiply by our dr by dt, which is 2t. And then in one step, we're going to put together our constants. We have a 2 pi and a 2, and so we get a 4 pi. And what's left is r and t. And in general, it's quite nice to see, for example, dA by dt in terms of the independent variable t, whatever we're differentiating with respect to. So we have this rt at the end, but it's nice if we can write r in terms of t. And well, we can, because we have our r equals t squared plus 1. And so our r times by t becomes t from the t here, multiplied by t squared plus 1 from the r. And this is a nice factorised form of dA by dt. Let's take a look at some examples. Our first example tells us that given that y equals x squared plus 4 all cubed, we're asked to find an expression for dy by dx in terms of x. Our first step is to convert the function into a composite function by introducing a new variable in terms of x. Currently, we have that y is equal to x squared plus 4 all to the power of 3. If we take our x squared plus 4 to be the new variable u, then we can write y as equal to simply u cubed. Our second step is to find du by dx. This is because we're going to aim to use the chain rule. So again, in particular, we have defined u to be x squared plus 4. And so when we differentiate and get du by dx, this is going to be 2x by differentiating. Our third step is to find dy by du. We have that y in terms of u is y equals u cubed. And so dy by du is going to be equal to 3 multiplied by u squared. Our fourth step is to recall the chain rule for composite functions. If we want to calculate dy by dx, then we can do this by introducing a new variable u in terms of x, and we get that dy by dx is equal to dy by du multiplied by du by dx. Our fifth step is to use the chain rule to find dy by dx in terms of x. So using the above chain rule, we get that dy by dx, just by substituting in, is going to be equal to dy by du, which is 3u squared, and then we multiply by du by dx, which is 2x. We can bring all the constants to the front, and so we get a 6 for the outside constant, and then we have our x, and all we're missing now is our u squared. Well, by definition, u is equal to x squared plus 4, and therefore we have as our u squared, by substituting back in, x squared plus 4 all squared. This is our result for dy by dx. Our second example tells us that given that y equals 3 lots of 7 minus x to the power of minus 5, we're asked to find the value of dy by dx at x equals 1. Our first step is to convert the function into a composite function by introducing a new variable in terms of x. At first we have that y is equal to 3 lots of 7 minus x to the power of minus 5. If we let u be 7 minus x, then we get that y is simply equal to 3 lots of u to the power of minus 5. And so our second step is to find du by dx, because we're aiming to use the chain rule. Since we have that u is equal to 7 minus x, simply differentiating, i.e. du by dx, will give us minus 1, because we have this minus x here, which differentiates to minus 1, and the 7 disappears under differentiation. Our third step is to find dy by du. We have that y is equal to 3 lots of u to the power of minus 5. And so by differentiating, i.e. obtaining dy by du, we get a minus 15 for our outside constant, and then we have a u to the power of minus 6. Our fourth step is to recall the chain rule for composite functions. We have that dy by dx, which we're hoping to find, is equal to, when we introduce a new variable u in terms of x, dy by du multiplied by du by dx. Our fifth step is to use the chain rule to find dy by dx in terms of x. And so we get that dy by dx, by substituting in our expressions for dy by du and du by dx, dy by du is minus 15 multiplied by u to the power of minus 6, and then we multiply by du by dx. Du by dx is simply minus 1. And so bringing the constants back together, we get a plus 15, and then resubstituting back for u, we have that u is 7 minus x, and so we get this multiplied by 7 minus x to the power of minus 6. Our last step is to substitute x equals 1 into the equation for dy by dx. In the question, we are asked to find the value of dy by dx at x equals 1. And so when x equals 1, the value of dy by dx, by looking at our expression for dy by dx that we derived above, is going to be equal to 15 multiplied by 7 minus the 1 from the x to the power of minus 6. And so we get, and since 7 minus 1 is 6, we have 15 times 6 to the power of minus 6, and as a fraction, this is 5 divided by 15,552, and as a decimal is equal to 3.22 times 10 to the power of minus 4 to 3 significant figures. Our last example tells us that fluid flows out of a cylindrical tank with a constant circular cross-section of radius r. The square root of the volume V of the remaining fluid is proportional to the rate at which the fluid is flowing out. We are asked to find a general expression for the rate of change of the depth h of the fluid in the tank given by dh by dt. Our first step is to form an equation relating the volume V and the rate of fluid flowing out. We've been given in the question that the rate of fluid flowing out, which is dV, the volume, by dt, the time, is proportional to the square root of V. And therefore, this means we can write that dV by dt is equal to minus k lots of the square root of V. Now this is for some constant k goes to 0, and the reason we have a minus here is because we want to have k being strictly greater than 0, and also that we're told that the fluid is flowing out. And the reason we have a negative symbol is because we want to have k strictly greater than 0, but also the fluid is flowing out. And dV by dt is the rate at which the volume changes. Flowing out corresponds to decreasing volume, and therefore we need to have a minus sign to accommodate for that. Our second step is to find an equation relating the volume V, radius r, and the depth h of the fluid. We have that the cross-sectional area of the tank is equal to pi multiplied by r squared. Now, because it's a cylinder, the volume V is equal to the depth multiplied by the cross-sectional area. And therefore we get that V is equal to the cross-sectional area pi r squared, and then we multiply by the depth, which has been given as h. Our third step is to differentiate to find dv by dh. We have that v is equal to pi r squared multiplied by h. Now, one thing to note is that in the question, we have been told that the radius r is constant, and therefore we should treat it as such, and so when we differentiate v with respect to h, we get dv by dh, and this is equal to simply pi r squared, since all of this pi r squared is just a constant. Our fourth step is to use the chain rule to form an equation involving the calculated rates of changes. In the question, we've been asked to find an expression for dh by dt. So we write this first, and then we can use the chain rule to express this in a slightly different way. All we need to remember is to use fractions throughout, and therefore we have a dh here and a dt here. The thing in between is up to you. In this case, it is sensible to use our dv, since we have a v involved. And therefore we're going to have a dv both here and here. So one thing to note is that we have dv by dh and not dh by dv. But this is not a massive issue, since dh by dv is 1 over dv by dh, and so we get 1 over dv by dh, which is something we have, as above, and this whole quantity is multiplied by dv by dt. Our fifth step is to find an expression for dh by dt in terms of v, k, and r using the chain rule. So our new version of the chain rule is that dh by dt is equal to 1 divided by the whole thing of dv by dh, and then we multiply by dv by dt. Now what we need to do is to substitute in our results. dv by dh we have as equal to pi r squared. So we get a 1 divided by pi r squared in accordance with the formula. And then dv by dt we found right at the beginning was equal to minus k root v for some constant k strictly greater than 0. And so we multiply by this minus k multiplied by root v. And therefore we bring it all together and we get a minus k divided by pi r squared, and then we have the root v. And we should mention that k and r are constants. We would have to know the value of r and know some more information to be able to find the value of k, but in particular it's useful to know that dh by dt is just proportional to the square root of v.
Hey guys, I hope you enjoyed the video. If you are looking for an amazing A-level maths resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face and together let's make A-level maths a walk in the park.